Hi, my name is Philipp Schaad. I'm with the Scalable Parallel Computing Laboratory at ETH Zurich, and I would like to present FuzzyFlow, which is a novel approach we have developed to help you find and squash program optimization bugs automatically. So in a modern HPC landscape, the compiler plays a very fundamental role in getting the code written by some domain scientist to perform adequately on a particular target system, such as a supercomputer. This is because compilers have sophisticated automatic optimization passes that can get a lot of performance with very minimal effort out of an application. The issue with these automatic optimizations is that they have to be rather conservative just simply because the compiler does not know all of the program parameters and consequently has to be rather careful to not change what the actual application is trying to perform while trying to perform optimizations. And this is where the role of a performance engineer comes in, which is a human optimizer that essentially tries to hook into this process at various stages to squeeze more performance out of the application than the automatic optimizer can. This is done sometimes by modifying the original source code directly, by optimizing on some intermediate representation that the compiler uses internally, or even in some cases to modify the generated code in a very low-level optimization scenario for particular target architectures. In modern frameworks such as MLIR, it is even sometimes possible to write custom optimization passes that the compiler can then apply repeatedly on a larger scale. This is very often done for particular classes of applications or a particular class of systems. But the problem with all of this is that while the automatic optimizations that are performed by optimizing compilers are very well studied and tested, the same does not hold true for the optimizations that are performed by a performance engineer. There's human error, of course, that can sneak into this, but it's also just by the nature of these optimizations being very bespoke and specific to a particular system or a particular type of application that it's very hard to test these for the general purpose. And this makes it difficult and time-consuming to author tests even for a specific application to verify that the optimizations are actually performed correctly. This is where we come in with FuzzyFlow, with which we are setting out to actually automate this form of testing for custom program optimizations. So before we can actually discuss how we achieve this, let's first formalize what we consider to be an optimization. In a general case, we can say that if we have some program P, in our case here we have a simple matrix-matrix multiplication between two n by n matrices, we can apply some transformation or translation to this program, which takes the program and performs a structural change. In the case here, we have some tiling by a tile size of 32. And then we arrive at a structurally different program P prime. Now, optimizations are a very specific kind of these translations. For one, of course, they try to achieve an improvement in performance. But more importantly, while achieving this improvement in performance, we usually don't want to change what the application does. So optimizations, we can say, should in general preserve the program semantics. So how can we specify what we consider the program semantics? Well, in our case here for the matrix-matrix multiplication, we have some input configuration. In this case, this would be the size parameter n for the matrices and the matrices A, B, and C. And if we feed this input configuration into our multiplication, we would essentially get out a result matrix C, but also the program would exit with some specific exit code. Usually this will be exit code 0, or if the program crashes, this would be something different. And we can summarize both of these things together as being the system state of the program P given some input configuration X. And now if we specify that an optimization preserves the program semantics, we would expect to say that if we feed the same input configuration X into the program, the transformed program P prime, we would get out a different system state, S prime, which is a different result matrix C and a different exit code, but that this system state S prime would be exactly equivalent to the original system state S. And if that's the case, we would essentially have a program that performs the same semantically equivalent computation. Now, the astute among you might have already noticed that for the optimization that we have actually performed here, the tiling with tile size 32, the program or the optimization is only correct for input parameters n that are a multiple of 32. So the optimization is only correct for some inputs and not for others. If we provide an n that is not a multiple of 32, we would either get a different result matrix C, or more likely we would get a crash, such as a sec fault, which would lead to a different exit code, which means that the system state S prime would not be equivalent to the system state S, and this would indicate a change in semantics. So how can we actually automate the testing to detect such changes in semantics for an arbitrary program P and an arbitrary transformation T? Well, there are different forms of approaches that we can use here. One common technique is to use formal validation, which is, of course, giving us a proof on the correctness of T. But the problem with this is that it requires specifying both a formal specification for the language that we are actually working with, as well as the transformation or translation rule T. And this is extremely time consuming. And also importantly, it's difficult to detect the correctness of, or to detect input dependent correctness. So we have already discussed that this is a correct transformations if n is a multiple of 32, but not otherwise. And this kind of input dependence is hard to validate with formal correctness proofs. An alternative is to go back to the specification of what we consider to be semantic equivalence that we have just talked about, which is that if we feed in some input configuration x into both the transformed and untransformed program, we would expect to see a matching system state coming out of these two applications. And this is a general approach of using this information is what we call differential testing. So we would feed in an input configuration to both programs and check that the system state is the same. This can also be performed with various techniques. A common one is to use symbolic execution, which essentially avoids actually executing the application, but uses symbolic arithmetic to determine what possible values of different program data containers would be at different states of the program. However, the issue with doing this is that this usually requires full source information, and especially in an HPC context where we are trying to optimize for specific applications or specific computations and target systems, we would very often have architecture-specific intrinsics, such as for tensor operations and so on and so forth, where we do not have full source information, meaning that it's difficult to perform symbolic execution on these parts of the application. An additional issue with symbolic execution is that we very quickly run into a space state explosion, especially in the context of many nested loops, such as we have in this case here. And finally, in HPC, we are very often dealing with floating point arithmetic, which is something that symbolic execution, at least in the current state of the art, is not very well equipped to deal with. An alternative approach to make use of differential testing is to actually use a technique that is common in information security, which is to fuzz the input or to perform fuzz testing. The idea here is that you actually sample a large number of different input configurations and then run the actual application with these input configurations and check for an equivalent system state in many of these cases. Now, of course, this is no longer a formal correct or a guaranteed correctness, but rather it is probabilistic testing. So you are just very likely to uncover an issue and you're not guaranteed to uncover it. And there's a second issue with this that is especially relevant in an HPC context, and that is you have to actually execute the application for each input configuration, which in the context of HPC applications that can take hours or sometimes even days to execute is just simply not practical if you have to sample hundreds or thousands of input configurations. And this is where we actually come in with FuzzyFlow, because we managed to solve both of these issues of probabilistic testing and the execution taking a large amount of time to provide a technique with which we can fuzz test, perform differential fuzzing to find program optimization bugs more than 500 times faster than if you were to perform differential fuzzing on the entire application. So let's look at how we address these issues by first looking at how we solve the problem of execution taking a large amount of time. So in a realistic context, we usually have something a little bit more complicated than what we had before. This is, of course, still a relatively simple example, but it's a similar problem to what we had looked at before, a chained matrix multiplication of matrices A, B, C, and D. And we performed the same optimization of a tiling by a tile size of 32 of the second multiplication in this chained matrix multiplication. And now the key realization here is that if we have an optimization like this, it's rarely the entire program that is affected by the transformation, but rather we have a very small subset of the entire application that is actually changed by the transformation that we're performing. And so the key realization here is that rather than testing the entire application, what we could do is we can sort of cut out this part of the application, which would give us a little small individual test case or a program cutout, which is a subset of the original program. And then we can apply the transformation or optimization only on this little subset of the program to arrive at a transformed version of that little cutout, which we can then use for differential testing, giving us a much smaller application to actually run as compared to the original. So let's look at how we can actually extract such a program cutout for differential testing given a particular transformation T performed on our program. So while this starts with actually identifying the lines that were modified by a particular transformation, which you could do with a program diff, and then cutting them out into a separate program, we can't stop just there. The important part to remember is what we're trying to do is we're trying to feed an input configuration for our transformed and untransformed program, and then compare the system state for this input configuration afterwards to check for equivalence. And so what we essentially have to do is, for a particular set of changed lines, we need to identify what we have to consider the system state to check for equivalence, and what we have to consider the input configuration for that part of the application. So sort of informally, we can say that the system state is anything that will have an impact on the behavior of the program after our change or on the rest of the program, while the input configuration is everything from before that will affect the behavior of the actual program cutout that we have extracted. And so if we look at the example that we have here, what we can say is that for the given program cutout that we have, only what remains in the matrix V after execution of the cutout will actually have an influence on the rest of the program, because V is the only data container that is being read later on and may influence the actual overall output of the program, in our case the matrix R. So we can say that the matrix V will be part of our system state. Now, inversely, to determine the input configuration, we can say that obviously the size of the matrices will have an influence on the behavior of our program cutout, but then also the contents of the matrices U, C, and V will determine how our program cutout behaves. And so essentially we have to say that all matrices V, U, and C, as well as the input parameter N, will be the input configuration for our program cutout. Now, for this simple case, it's obviously relatively easy to do this manually, but the problem is that finding this for an arbitrary program change, especially in high-level programming languages, can be relatively hard. Essentially, to do this, we need to perform a detailed side effect analysis. We need to analyze how changes to individual scalars may affect the program behavior at a different location. We need to determine how changes to an individual memory location may change the program behavior in a different location, but also how changing just an individual little subregion hidden behind a pointer may affect the program behavior at a different point. And so because of pointers, this is relatively difficult to do. So you could have pointer aliasing that makes it difficult to detect memory side effects, or you could have pointers that point to overlapping memory regions, which makes it very difficult to detect side effects from changing individual program subregions. There's an additional problem that makes this a little bit hard. We have already said that for determining the correctness of the transformation that we have seen here, such as the tiling with a tile size of 32, this is only correct for a particular type of input or for a particular input size. And so not only do we need to perform a side effect analysis to determine the input and output configuration or system state, but rather we also need to be able to generalize the test case that we extract for different types of inputs. So this is what we will do with fuzz testing essentially, but also for different types or for different sizes of inputs. And this again is not trivial, because if we look at the extracted program that we have here, especially in this representation that we have right here, it is basically impossible to determine that there is a size or a relationship between this variable n and the sizes of the matrices that we are working with. Of course, using human intuition or knowledge about the application, we can tell, but in the general case, this is difficult to do automatically. So because of this challenge to extract a general test case for an arbitrary program change, FuzzyFlow actually leverages the parametric data flow representation of an application to extract program test cases. So what this means is that the first step in actually extracting a test case for us is to build a parametric data flow representation of the program, which essentially is a graph-based representation of the application, where we have graph nodes that represent data containers, and they represent computations and loop nests that contain them. And then we have directed edges that represent data movement and data dependencies between individual computations and data containers. A keyword in this is also that this representation is parametric, meaning that individual data accesses are expressed with symbolic expressions with respect to some program parameters. So in our case, one of the program parameters is the size parameter n for the matrices. And this allows us to reestablish this relationship between the size of a data container and a program parameter, in this case n, which shows us that, for example, the matrix V is a matrix of size n by n, where n by n is some symbolic expression that we can perform symbolic reasoning on. And so the first step in actually extracting a test case in this parametric data flow representation is to again look at what the changes were that are made by a particular transformation, and then identifying the exact program graph nodes that correspond to the changes made by the transformation. We can then take these program nodes and cut them out into an individual little program graph. And now we can use the power of the data flow representation to isolate the direct data dependencies of this change. So essentially all we have to do is we have to look at the data container nodes that are directly connected through data movement edges to the nodes that were modified by a transformation, and the specific subsets that are accessed across these data movement edges. And then we copy those over into our program test case to arrive at a program cutout that fully contains the changes made by a transformation and the direct data dependencies that are affected by this change in the transformation. And so now to fully isolate the actual effects of the transformation, we need to perform our side effect analysis to determine the input configuration and the system state. And again, for the input configuration, this basically means everything that can come from the outside and influences the behavior of our program cutout C. And so in a data flow context, what this means is that the input configuration is essentially anything where we have a read inside of our program cutout C from a particular memory location or memory subset, where we don't have a preceding write to the same memory location or overlapping memory location in our program cutout C. And so in our case here, essentially we have reads from the matrices V, U, and C, and specifically the entirety of these matrices, and we're not previously writing to those memory locations in our program cutout, and so the matrices V, U, and C are part of our program input configuration. Additionally, with the parametric representation, when we know that, for example, the matrix U is a part of our input configuration, we can also see that there's a program parameter n that this matrix U depends on, and so this program parameter n is also part of our input configuration. And now for the system state, essentially, again, this is anything that we modify inside of our program cutout C that may have an influence on the rest of the program P. And so in a data flow context, this is essentially anything where we have a write inside of the program cutout C and then a subsequent read inside of the program P. And in the data flow context, this means that we can determine a subsequent read by just simply performing a graph reachability analysis or a graph traversal starting at our program location or a program cutout C in the original program and looking for any reads that we can reach from that point. So in our case here, we can see that there's a read from V on the entire subset of the matrix V, and we are writing to an overlapping memory region inside of our program cutout, which means that the matrix V will be part of our system state and needs to be checked. And so as you can see, this means that by using this data flow representation, we essentially essentially allows us to perform a detailed side effect analysis, and we are able to perform or to analyze the input configuration and system states for an arbitrary change in the program. But not only that, because of the parametric nature, we have also gained the ability to essentially generalize this test case that we have extracted for arbitrary inputs and input sizes. And so by doing this, we essentially can extract for any change performed on an application a minimal test case that fully contains all of the side effects that this change might have on the rest of the program into a small test case that takes much less time to execute than the entire application. And essentially, this means we have solved this part of the differential testing problem that we have outlined before. So let's look at how we address the second problem with fuzz testing, which is that we are dealing with probabilistic testing, meaning that how likely we are to find a problem in a transformation depends on how well we are covering the space of possible inputs in our fuzz testing procedure. And so what we want to do is we want to reduce the space of possible inputs as much as we can. And to illustrate the effects of this and how well we are, or how we can do this automatically, I have a didactic example here where we have a sequence of computations and a transformation that inlines two of these computations to remove a temporary variable temp. Now, looking at our procedure from before, we essentially construct a data flow graph for our application. We identify the nodes that were changed by the transformation T, and then we copy them as well as any direct data dependencies out into a program cutout C. Now, a benefit of using the data flow representation for this, or the parametric data flow representation, is that we can see that we're not actually modifying the entirety of the vector c with our computations here, but rather we're only modifying a scalar subset of the vector c. And so we only have to copy that over into our program cutout, giving us a much smaller system state that is not the entirety of the vector c, but only an individual scalar value. So we essentially get an input configuration consisting of two 32-bit integers, the integers y and z, and a single scalar c at the index I that is our system state. Now, even though we only have two scalars as part of our input configuration, this already gives us a huge amount of possible inputs that we would have to sample from. And what we can see if we look at the data flow graph is that if we were to include the additional computations behind the functions f and g, we would actually get a much smaller system, or a much smaller input configuration already, which would also allow us to cover the input space much better. And so how can we automatically find this kind of minimal input configuration for a particular change to the program? Well, informally, we can say that this is kind of the tightest point of the graph that we have for a given change in the application. More formally, this essentially corresponds to an ST minimum cut between the program start and the cutout that we would get for a particular change in the transformation. And so to do this automatically, or to determine this minimum input configuration automatically, we essentially insert a virtual source node that represents the start of the application, and we connect it to any previous data containers that don't have any incoming edges, and we annotate the edges there with the size of the data containers that we have connected them to. So in this case, we have two vectors a and b, each of size n. We annotate them with the size parameter n. Next, we essentially replace the original program cutout that we would get with a virtual sync node, and we annotate the edges going into that virtual sync node with the size of the original input configuration that we would get. So in this case, we have one scalar value that is being read across each of these input edges going into the cutout. Next, we annotate all outgoing edges from data containers with infinity. We do this because we essentially never want to cut across one of those edges because that would sever a data dependency. And then finally, we annotate each remaining data movement edge with the number of data elements that are being moved across it or that depend on this data movement edge. And now finding the minimum input configuration essentially corresponds to running an efficient minimum ST cut algorithm such as Edmonds Carp, which will efficiently find the point in the graph where we have the minimum ST cut. And if we cut at that part of the graph, any node that is now no longer reachable by the program start S will be added as part of the program cutout, which will give us, in this case here, the much smaller input configuration of the single scalar value x. So not only is it important to reduce the size of the input configuration space, but we can do a little bit better than that even. To illustrate this, there's another didactic example here in which we essentially have two computations happening inside of a function foo, and then there's a transformation that inlines these computations again to remove a temporary variable. And if we look at this, this gives us a program cutout that corresponds to only the two computations that we inline with an input configuration of this matrix C, the two variables I and j, and a system state that corresponds to the matrix C. Now, one thing that we can see immediately is that I and j are actually used to index into the matrix C. And if we assume that the matrix C has some size 50 by 50, if we sample random values for the input parameters I and j, this will mostly lead to uninteresting crashes in the sense that we are essentially just indexing out of bounds and causing segmentation faults that have nothing to do with the transformation that we have actually performed here. And so what we can do to address this issue and to increase the probability to actually find interesting crashes or relevant crashes in that sense is we can constrain any input parameters that are used to index into a data container to the size of that data container. So in our case here, we would essentially constrain the variables I and j to the interval between 0 and 50, or 49 more specifically, to avoid having crashes that would crash both the original program and the transformed cutout, just simply because we're indexing out of bounds. However, we can see if we look at the original application, because foo is being called inside of a different part of the application, that there's actually a further constraint on this parameter j. So we can analyze the control flow of the application to further derive constraints for the for individual input parameters. So in our case, we can refine the constraints around parameter j to actually only be in the range from 0 to 19, because this is the only values that this parameter might take on in a realistic scenario. Now, in addition to minimizing the input configuration and constraining individual inputs, there is one more case that we need to consider. If we look at the test case here, which has an input configuration of the variable x, if we just randomly sample variables for x, it is very likely that we will not ever execute half of the application in this test case. And so to address this, we actually use our Dataflow cutout to generate a C++ version of our test case, as well as a single sampled input configuration, and feed both into this into a coverage guided fuzzer such as AFL++, which essentially instruments the code and then mutates the input configuration that was provided in such a way to try to maximize coverage of the test case that has been provided. And so by minimizing the size of the input configuration space, constraining individual input parameters, and maximizing the test case coverage, we have essentially addressed the issue with probabilistic testing and drastically increased the likelihood with which we will find uninteresting crashes, or with which we will find crashes in our application. So with these problems addressed, let's look at how FuzzyFlow actually automates this process of finding program optimization bugs and then helping to debug them. Essentially, given some program P and an arbitrary transformation T, FuzzyFlow starts by extracting a program cutout C that captures all the changes made by the transformation. It then applies the transformation to this program cutout and then samples an input configuration over the space of possible inputs using uniform sampling and respecting the program constraints that we have derived, or it mutates the input configuration to maximize coverage. The cutout is then run both in its original and its transformed version on this input configuration, capturing any crashes that might occur in the meantime, and then the system state is compared and checked for equivalence. Now, specifically, we consider a system state to be equivalent by using numerical difference checks, and if the numerical difference is below some user-provided threshold T delta, then we consider the system state to be equivalent. If this T delta is set to 0, we are of course checking for bitwise equivalence. The steps 3 to 5 are then repeated R times, where R is the number of samples that you want to perform. This is also a user-provided variable. And then at the end, if there is a bug if any of these tests that were run actually results in a different system state, we essentially have a counterexample with a specific input configuration that shows you where your transformation might have introduced a problem and helps you in debugging with a minimal test case. So using this procedure, we build a proof of concept implementation of FuzzyFlow in the optimization framework DACE, which is a data-centric optimization framework that has been used with great success and provides a lot of automatic optimizations for real-world applications. And we go on a little bit of a bug hunt with this. Specifically, we look at the numerical Python benchmarking suite NPBench, which is a collection of 52 benchmarking applications specific to HPC. And we essentially use this to run all of the automatic optimizations that DACE offers, which is a collection of 61 individual transformations and passes, and use this to extract test cases on all of these 52 benchmark applications. So in total, this results in 3,280 test cases that we can extract. And by running FuzzyFlow on all of these 61 optimizations that DACE contains, we did find that 6 of the transformations included in DACE contain bugs in one case or another. Specifically, there are 2 of these transformations that actually change program semantics in specific scenarios, and there are 4 transformations that lead to invalid code being generated when they are applied. Now, to evaluate our method of automatically reducing the input space, we look at an additional example. Specifically, we optimized the encoder layer of the BERT natural language model with DACE. And what we found here is that DACE essentially tries to vectorize a parallel for loop, or a loop nest of 4 nested parallel loops. And with FuzzyFlow, this results in a cutout that contains these 4 nested loops and an input configuration of a 4-dimensional tensor temp, as well as a scalar variable scale, and a system state that also contains a single 4-dimensional tensor. Now, when we run the automatic input minimization, what FuzzyFlow includes in the cutout is a preceding batched matrix multiplication. Now, on first glance, this actually increases the input configuration space by replacing the temporary transient with 2 other transients, x and y. But if we look at the actual input configuration that is being used or the program parameters that are being used, this reduces the input space by 75%, leading to the ability to run more than 43 trials per second on consumer hardware. This corresponds to a speed up of more than 528 times with respect to running the entire application, which takes more than 12 seconds. Finally, let's look at an example where performance engineers were trying to optimize ECMWF's Cloud Microphysics scheme, or Cloud SC. Specifically, what they were trying to do is they were writing a transformation for DACE that would automatically extract GPU kernels and generate the necessary CUDA boilerplate as well as the kernel launch calls. And a problem was uncovered here where essentially the kernel that is being extracted only writes to a particular subset of a data container, but in the transformation, they generate CUDA boilerplate with which they copy back the entirety of the data container from the GPU, meaning that potential results that were computed on the host are being overwritten with garbage data from the GPU. This is a bug that took the engineers more than 16 hours to find and debug, and we tried to replicate this with FuzzyFlow, and essentially by running this transformation through FuzzyFlow, FuzzyFlow was able to detect this issue within 43 seconds on consumer hardware and generated a test case that would help debug this problem. So to conclude, we have presented FuzzyFlow, which is a technique with which we can find program optimization bugs more than 500 times faster compared to traditional methods. We have seen how we can use the parametric data flow representation to extract minimal program cutouts that contain only the changes made by a particular transformation, how we can automatically reduce the input space as much as possible to improve fuzzing efficacy, and finally, how we can use this in practice to find program optimization bugs and generate test cases that help in debugging. This entire project is open source, and if you want to learn more, you can go to the GitHub repository where we have the source code for this application, and you are welcome to check out the remaining talks at SPCL for more information on our research. Thank you very much.